Hello everyone. In today's video, we are going to dive into random forest classification in GEE. It's a powerful tool in machine learning, helps categorize data into different classes. Let's break it down step by step. Building decision trees. Firstly, the algorithm creates numerous decision trees. Each tree uses a random subset of training data and features. Think of these trees as a series of questions, like if this, then that ultimately classify a data point. Introducing randomness. Now, why random? Well, by picking different data and features randomly for each tree, we prevent the model from becoming too good at the training data but bad at the new data. This randomness helps combat overfitting, a common issue in machine learning. Making predictions. Once we have built all the decision trees, a new data point goes through each tree. Each tree then makes its own prediction about which class that data point belongs to. Finally, the most common prediction among all trees becomes the final classification for the new data point. Advantages of random forest classification. Let's talk about the pros of random forest classification. High accuracy. It can achieve impressive accuracy on classification tasks. Then robust to overfitting. Random forests are great at handling overfitting. Then handles missing data. They can effectively deal with missing data points in the training dataset. Feature importance. The algorithm provides insights into the importance of different features in the classification process. Disadvantages of random forest classification. Black body model. Random forest can be complex, making it tricky to interpret how they make predictions. Then, high computational demands. Building large random forests requires substantial computer power, especially with the big datasets. And now we are diving into some exciting GEE Google Earth Engine code used in our recent paper titled Improving Crop Classification Accuracy with the Integrated Sentinel-1 and Sentinel-2 Data, a case study of barley and wheat. Published by me, Azad Rasool, Dr. Gailan Ibrahim, and Dr. Heidi Abdullah. If you utilize this code for your research, please consider citing our paper titled Improving Crop Classification Accuracy. Flowchart methodology. Before we jump into the code, let's take a quick look at the methodology we used. We have prepared a flowchart to give you a visual understanding of the steps involved in our research process. We have data collection from Sentinel-1 and Sentinel-2, then pre-processing data, create mean VH and VV, select band, blue, green, red edge, and near bands, then combination them, dividing our data, for validation and training samples, then apply random forest and card classifier, find accuracy assessment, finally crop type classes. Output maps. Next, we will showcase some output maps generated from our analysis. These maps provide valuable insights into the classification results and highlight the distribution of barley and wheat crops in our study area. In the left side, we have classifier from SAR, then classifier from optical image, and the C is combination of optical and SAR image with the high accuracy. In this slide, we have compare overall accuracy between different methods. This comparison is crucial for evaluating the effectiveness of our approach and determining the most accurate classification method for crop classification. SAR random forest 72.7, SAR from cart method only 65%, Sentinel-2 random forest 89%, and Sentinel-2 cart 85%. Then combination of SAR and Sentinel-2 from random forest classification 94%, and combination of SAR and Sentinel-2 from cart classifier 89% accuracy. And that's confusion matrix of the classification result using SAR and Sentinel-2 from RF classifier. For example, this wet pixels which is correctly classified, then some pixels merged with the barley, and some pixels with the uncultivated land, and so on. The overall accuracy is 95% and kappa is 0.91. Let's get started with the code. First, we will work with the Sentinel-1 SAR synthetic aperture radar data. We are specifying loading the C-band SAR ground wrangle collection from both VV vertical and VH vertical horizontal polarization. We filter these collections based on instrument mode, polarization, orbit direction, resolution, and region of interest ROI. Then we clip the images to our ROI and select the VV or VH bands. Next, we filter the SAR collections by date, focusing on a specific range. We create mosaics of VV and VH images for this date range. To visualize these images, we added them as layer to the map. We set center and zoom parameters to 12, then display the SAR VV and VH layers. Moving on, we apply a filter to reduce speckle in the SAR images. We use a focal mean filter with a specified smoothing radius. We name it SAR VV filtered equal SAR VV dot focal mean smoothing radius. Then var SAR VH filtered SAR VH with the method focal mean smoothing radius. After that, display the filtered SAR images. Now let's run this part of the code. We have SAR VV and SAR VH layers. And that's it. We have successfully loaded filtered and visualized SAR images using GE. Now let's move on to Sentinel-2A. First, you will start by masking out clouds and cirrus in Sentinel-2 imagery. This helps us get clear images for our analysis. We will use a function called mask2clouds to do this. It selects the quality assessment bands QA60, define cloud and cirrus bits, and creates a mask to indicate clear conditions. Then we will load the Sentinel-2 imagery, filter it by date and cloud cover. For cloud cover, we filtered smaller than 5%. Then apply the cloud masking function we just created and clip it to our region of interest, ROI. Now, let's visualize the Sentinel-2 imagery on the map. You'll set some parameters for better visualization and add the imagery to the map. We can also get some basic information about the imagery by printing it. Next, we will take the mean of the Sentinel-2 imagery. This helps us get a clear picture by reducing noise and variations. Let's run this part of the code. The bands we have in the image from B1 to B12. In the same way, we created a collection 2 for Sentinel-2 imagery. That's the true color of Sentinel-2 of our study area. Calculate NDVI. After processing the imagery, we move on to calculate the normalized different vegetation index NDVI from the Sentinel-2 data. NDVI is a key metric for assessing vegetation health and density. We will use the near infrared, near and red bands to compute NDVI. Then we will create a composite image that includes all the Sentinel bands along with the calculated NDVI. To display these images, we added them as layers on the map. This allows us to visually inspect both Sentinel-2 composite and the NDVI layer. Let's run the code again. For apply the RF random forest classification, we created different types of feature collection, for example, barley, wheat, uncultivated land, road airport, bare land, and grassland. For example, for barley, we have 25 features collected in feature collection in the type of polygon. In the same way, we selected 100 elements for representing wheat. How it be created? For example, for creating a new layer. We're going to geometry imports, then click on new layer. We edit layer properties. Let's name it, for example, test 1, and geometry is feature collection. And in the property, for example, line cover, and here number of the class, it starts from the 0. Let's say this number 7. And let's say we go to this part of our image to select some polygons and some points that represent this class. SAR classification. Now let's delve into SAR classification. You'll start by merging various feature collections representing different land cover types into one cohesive collection. This merged collection, named new FC, will serve as our reference for training the classifier. Next, we'll define the SAR bands to train the data by combining the filtered SAR images from SAR PV and SAR VH into one image called final. We create a comprehensive data set for classification. The selected bands for training are VH and VV. To train our random forest classifier, we will sample regions from the merged feature collection and assign random columns. These sampled regions are then split into training and validation data sets. We divided it by 70% and 30%. With the training data prepared, we process to train the random forest classifier using the training dataset. This classifier is then applied to SAR data to perform the classification. Then we will visualize the classified SAR image on the map, showing different land cover types with distinct colors. Additionally, we will classify the validation data to evaluate the accuracy of our classification process. For RF classification, we selected 60. You can play with this number to increase accuracy of your classification by increasing or decreasing this number. Let's run this part of the code. This is the output of random forest classification based on the only SAR imagery. Now let's move on to Sentinel-2 classification. We'll start by defining the bands to be used for classification: blue, green, red edge, and near. In addition to the spectral bands, we will also include the NDVI as a feature to increase accuracy. This comprehensive set of features will help us effectively classify land cover types. Next, we will sample regions from the composite image based on the defined bands and land cover properties. These sampled regions will then be split into training and validation datasets to facilitate the classifier training process. We'll train the random forest classifier using the training dataset, specifying the input features and the class property. Once trained, the classifier will be applied to the composite image to perform the classification. To visualize the results, we will edit the classified Sentinel-2 image to the map, assigning distinct colors to different land cover types. Additionally, you'll classify the validation data and print the confusion matrix and accuracy matrix. This step helps us evaluate the performance of our classifier on unseen data. After running this code for many times, we select 100 trees. You can play with this number by increasing or decreasing it or achieve more accuracy. Let's run this part of the code. Now we have results from Sentinel-2 classification and results from SAR classification. For example, let's look at this field. That's the field and how it's classified by the only SAR. Then how it's classified by the Sentinel-2. Regarding the accuracy, random forest classifier from Sentinel-2, validation overall accuracy is 0.89. After we classified our study area by using RF classifier with the SAR imagery, then with the Sentinel-2 imagery. Now for increasing the accuracy, now we combine SAR and Sentinel-2. Let's now combine SAR and Sentinel-2 classification. To achieve this, we will define both SAR and optical bands to train the classifier. This includes bands from the optical imagery blue, green, red edge, near, and NDVI index, as well as SAR bands, VH and VV. We name it bands opt SAR. We will sample regions from the merged feature collection using the defined bands and split them into training and validation datasets, 30% and 70%. Once the training dataset is prepared, we will train the random forest classifier using the training dataset, specifying the input features and the class property. After training, the classifier will be applied to the combined optical and SAR image to perform the classification. We selected 100 trees. Then we will visualize the combined classification on the map, masking out areas where either SAR or optical data is missing. Finally, we will classify the validation data and print the confusion matrix and accuracy matrix for both the training and validation datasets. This comprehensive evaluation will provide insights into the performance of our combined classification approach. Let's run this part of the code. Now we have layers with the SAR classification, optical classification, and merged optical with the SAR classification. The final method, RF based on the optical and SAR validation, achieved overall accuracy of 0.93 and kappa validation 0.89. We can zoom in to look at some pixels and fields. This is the classification of the field based on the optical classification. This is the result of our classification based on the only optical classification. This is the result of classification based on only SAR imagery. And finally, this is the result of classification of the fields based on the merged optical and SAR imagery. For example, this field is barley. We can use inspector and clicking on each pixels to look at it. It's classified to 0 class based on the SAR and optical, but based on the merged optical and SAR classification, it's classified to class 1. To complete our analysis, let's export the results to Google Drive. We'll start by exporting the classified Sentinel-2 as a GeoTIFF. This export operation includes several parameters such as the image to export, a description for the exported file, any name, the spatial resolution, 10 meters, the region of interest, ROI, or case study, and the folder in the Google Drive, and the maximum number of pixels to export. Let's run it. We click on Tasks and run this task. Now we can click on Open in Drive. That's our classified image. We can download it to our local computer. I hope you found this tutorial helpful. If you did, don't forget to like and subscribe our channel for more content. Until next time, happy coding!